Hey folks, in Lesson 8 we're going to start untangling some of these issues that we've been experiencing with multiple reference frames by introducing a very handy reference frame called the polar frame. So recall that we're starting to choose multiple reference frames, and I've told you before in class that it's because it really makes the process of solving these problems much easier. And so the simple pendulum has been our example, and recall that we used the simple pendulum and we solved it in Cartesian coordinates and in polar coordinates, both in the inertial reference frame. Now both those derivations were messy, and when we used Cartesian coordinates, the actual result, the equation of motion, was really messy. The polar coordinates had a really nice equation of motion, but it was tough to get to. And so we're starting to assign multiple reference frames to problems and to our system models. But one thing we haven't done yet is we haven't connected the coordinates in each of the reference frames. So we're going to start out by talking about the relationship between reference frames that rotate or are different orientations within the planes that we're working in. And we do that using a simple transformation. So in this class, we're only going to be working in a plane. So we have planar problems, and so that means that our reference frames can be reoriented with respect to each other. So here in this diagram that I took from the book, we have two reference frames. We have a reference frame A, we have a reference frame B. Our basis vectors in A are A1 and A2, and then our basis vectors in B are B1 and B2. And you can see that the reference frame B is rotated an angle of theta, that's a positive theta, so be counterclockwise, and that's in the A3 direction, a positive theta with respect to reference frame A. So, to be able to transform between these bases vectors, let's just draw these basis vectors right on top of each other. So here's what I mean. We have the A1 basis vector and an A2 basis vector. These are both unit vectors. And then we also have the B1 basis vector and then the B2 basis vector. Both unit vectors. And then we have that angle in between, theta and theta. And so if we want to write the basis vector B1, but we want to write that in terms of A1 and A2, then it's a pretty simple process. The hypotenuse of this triangle, okay, is 1 unit vector multiplied times the cosine theta in the A1 direction. So we've now defined that projection onto the A1 axis. And so we can continue in that process, and to project it onto the A2 axis, right here, then this is going to be a unit vector of 1 times sine theta in the A2 direction. And so we don't need our 1s, so we can say this is cosine theta in the A1 direction plus sine theta in the A2 direction. So we do the same thing for B2, that second basis vector in the B reference frame. And so for B2, projecting it onto the A1 axis would be over here. And so for B2, we get a unit vector of 1, and its sine theta is the magnitude of the projection, but it's pointed in the negative A1 direction. And so when we project B2 onto the A2 axis, then we get the unit vector 1 magnitude. Cosine theta is the magnitude of the projection, and that's in the A2 direction. And then we write that as negative sine theta in the A1 direction plus cosine theta in the A2 direction. And so what we can get from that is a transformation table that links the bases together. So we've defined now our B vectors in terms of our A vectors. And so let's just make a table out of this in which we say the A1 vector, the A2 basis vector, B1, and B2. And our table is cosine theta, sine theta, and then negative sine theta, and then cosine theta. And these are the coefficients that are coming from these parts right here. So if we put this in words, we're saying that the B1 vector can be represented as cosine theta A1 plus sine theta A2. And that's what we see right here. The B2 vector can be represented as negative sine theta multiplied times the A1 basis vector plus the cosine theta multiplied times the A2 basis vector. Likewise, we can reverse this and say that the A1 vector can be represented as cosine theta B1 minus sine theta B2, and the A2 vector is equal to sine theta B1 plus cosine theta B2. And so we now have, with this relationship, we can now convert easily between the basis vectors of any two reference frames as long as we know the angle theta, or the angle phi, or psi, or alpha, or whatever you'd like to use, but as long as we know the angle between these two reference frames in which they're rotated. Now, hopefully, by now, you are very comfortable with the idea that we can only apply Newton's second law in the inertial reference frame. And so that means that to do that, we need to calculate inertial kinematics, meaning that if we're going to be calculating if we're going to calculate the equations of motion for a point P, or a mass located at point P, we need to find the acceleration in the inertial reference frame to be able to apply Newton's second law. Likewise, our velocity, and to do that we have to also find our velocity in the inertial reference frame. But we can express these kinematics in whatever basis we like. Okay, so think about that just for a moment. We have to find the time derivative as observed in the inertial reference frame, but using our coordinate transformations we can express them in whatever basis that we want. And so often these basis vectors in rotating frames, just like we just defined, will provide a much more usable situation, much better information, and even more interpretable information simply by using those basis vectors. So for example, polar coordinates in an inertial basis for simple pendulum gave us beautiful equations of motion. Because if you remember, we used polar coordinates, we ended up with theta double dot is equal to negative g over L sine theta. That's something you can look at, you can interpret it, but remember that to get there, it was actually pretty rough going, because when we calculated our velocity in the inertial reference frame and our acceleration in the inertial reference frame, we ended up with expressions like this, where we said that the acceleration of point P in the inertial reference frame was equal to negative L theta double dot sine theta minus L theta dot squared cosine theta multiplied times the E1 basis, E1 vector, plus L theta double dot cosine theta minus L theta dot squared sine theta in the E2 direction. Okay? And so this wasn't hard to do. It took some bookkeeping like what we mentioned in class, but there were plenty of opportunities to make a mistake as we were taking all these derivatives, and this is very difficult to interpret. As I look at this scalar, I can't really break that apart easily and understand what that means. So we're now going to introduce the polar frame, which is going to allow us a lot more systematic and easier way to derive these equations of motion, and you'll see in the next class much more easy to interpret. So now let's define this polar reference frame, or this polar frame. And so let's start with something that we know. We've got an inertial reference frame, which we defined many times, in which we have an axis up, an axis to the right. We have our basis vectors E1 and E2, and then we call that the inertial reference frame I. And so in this reference frame, we have E1 that points to the right, E3 that's directly out of the page or out of the plane, and then our basis vector E2, which is the cross product of E3 crossed with E1. Now, the polar frame is going to be in a reoriented plane. or reoriented frame. So let's draw our point P. And so the polar frame is actually defined by the position of the point that we're interested in. And so it's a frame of reference that shares an axis with another reference frame, in this case the inertial reference frame, and then it's going to have a unit vector, or an axis in this case, that's actually pointing to the point of interest. Okay? So based on what we saw in this last little bit, we have an axis that goes through P. We have another axis that's 90 degrees to this. Okay? We're going to call this reference frame, we'll call it reference frame B. And then our unit vectors, we're going to have a unit vector that is pointed from the origin, in this case, to point P. We're going to call that unit vector E sub r. So we called this a polar frame, so we're going to be referencing polar coordinate system. So let's start defining these vectors. We're calling this reference frame B. It has an origin at O, so it shares the origin with the other frame in this case. It has an E sub r, we're going to use an E theta, and then we're going to use an E z, just like in our polar coordinates. And so let's define these basis vectors. E sub r is defined as along the line OP. So that means that between point O and between point P, it's always, this basis vector E sub r is always pointed there regardless of where P is. EZ we'll define as equivalent to E3, so that means that EZ is pointed out of the plane because we've defined E3 of that, just like that. And then E theta is going to be EZ crossed with E sub r. And so E theta, as we cross EZ, which is coming out of the plane, crossing with E sub r, gives us a unit vector pointed 90 degrees away from that, and so that's along this other axis. Now something to note in the polar frame is that E theta is always pointed and must always be defined in the positive theta direction. We've had discussions about this, about positive angles, negative angles. In this case, we're saying that positive theta is in the direction of E theta. So if you increase theta, then it's going to be in the direction of E theta. All right, so let's put, that essentially gives us our coordinates there, those polar coordinates. And then we have another polar coordinate because r is going to be the distance from point O to the particle. So we have our polar coordinates, and now we've defined a polar frame. One of the nice things about using a polar frame, or a polar reference frame in this case, is the ability to define the position of the point P. And so you can see here that r, our position vector, of P with respect to O, is simply going to be r, the scalar, multiplied times, or in the direction of, E sub r. And so that's really nice and easy to do. But remember, to apply Newton's second law, which is what we do, we always need to have our velocity and our acceleration in the inertial reference frame. Currently, our position vector is defined in the polar reference frame, which is a non-inertial reference frame. Remember, it's a rotating reference frame, so it's non-inertial. And so to get those kinematics, let's work through that. We've got v sub p. Our velocity of point P is observed in the inertial reference frame. Of d dt is observed in the inertial reference frame of r, p with respect to O. And this is equal to d dt observed in the inertial reference frame of the scalar r in the E sub r direction. Now when we take the derivative of this, we're going to get r dot multiplied times E sub r during the first part of our chain rule plus r multiplied times d dt as observed in the inertial reference frame of our basis vector E sub r. Now in the past, what we did is our basis vector, we used E1, E2, and E3, which were fixed in the inertial reference frame. So that meant that we could just say the time derivative of this basis vector was equal to 0. And in this case, we've got the time derivative of E sub r. And so because it's the time derivative of E sub r, this vector E sub r is actually rotating within the inertial reference frame. So it does have a time derivative, and we need to take care of that. So with a little bit of work, and you read about this in the book, and we'll deal with this in class as well, but with a little bit of work, we can see that d dt, the time derivative as observed in the inertial reference frame of the unit vector E sub r, is equal to, here's a new vector, it's omega b as observed in the inertial reference frame crossed with the unit vector E sub r. So what we said is that the time derivative of the unit vector E sub r, which is fixed in the reference frame b, is equal to omega b as observed in the inertial reference frame crossed with E sub r. And so this is where this omega, and so this is where omega b superscript to the right, I subscript to the left, is defined as the angular velocity of reference frame B as observed in reference frame I. All right? And so here in this particular case, omega b I is equal to theta dot, because that's the speed at which the reference frame B is rotating with respect to I, and that's in the E3 direction. Okay? It's in the E3 direction because that's our direction, that's our vector that's pointing out of the paper. And so this relationship is very handy. And also, we get one more that's related to it, d dt, as observed in reference frame I of E sub theta, is, you guessed it, omega b as observed in reference frame I cross with E theta. All right. So we got these two expressions that are worth memorizing because we'll use them frequently. And the general form for this, if we just want the generalized form, it's this. We're saying that d dt as observed in any reference frame A of B, where B is a unit vector, and it's a unit vector in frame B, is equal to omega of reference frame B as observed in reference frame A crossed with that unit vector in reference frame B. Okay, so let's say that again. The time derivative as observed in reference frame A of a unit vector that's fixed within reference frame B is equal to the angular velocity of reference frame B as observed in reference frame A crossed with the unit vector that's fixed within reference frame B. Alright, so let's put this to use, and let's go to our simple pendulum and let's solve one of these problems. Alright, so here we have our simple pendulum again, and we've got our reference frame, our inertial reference frame, set up the very same way that we have before, in which we've put the E sub 2 vector to the right, E sub 1 basis vector to pointing down. We've defined these E sub 1 as along OP when theta is equal to 0. That's a very good way to define this because it's based on the system. E3 being out of the plane, so let's draw that pointing out of the plane. and then E2 being the cross product of the basis vector E3 with E1. So now let's define our B reference frame, and let's start it also at the origin, and this is going to be our polar reference frame, so we're going to use an E sub r, E sub theta, and then an E sub z. So this reference frame, we've said it's always going to go from the origin to the point that we are interested in. So this is our B reference frame. And so our first basis vector, E sub r, is going to be equivalent to, we're going to define it as just along OP. It's not along OP only when theta is equal to 0, but it's along OP no matter what. We'll say that E sub z, let's put that basis vector on there. There's our E sub r. And then E sub z is going to be, we're going to set that equal to E sub 3. So E sub z is also pointing out of the page as a result. And then E sub theta is going to be equal to E sub 3 crossed with E sub r. We said that this now needs to be in the direction of positive theta, and we see that it is here because we have Ez, oops, let's see here, let's erase this, this is Ez, rather, crossed with E sub r, and so this is in this direction. So here's our E theta. We see that that does line up with what we've already defined as positive theta. There's theta there to finish out the relationship. So now we need to define the relationships between the reference frames. And we've talked about two of these. We've got one in which we can transform between these basis vectors, and then we just now defined a relationship of the angular velocity of a reference frame observed in another reference frame. So for the first one of these, we need to draw some basis vectors. So that's going to be our basis vector E sub 2, and then our basis vector E sub 1, unit vectors, and then E sub r, and then E sub theta. These are related by this angle theta. And then let's write these unit vectors in terms of each other. So E sub r, defined by E sub 1 and E sub 2, is going to be cosine theta E sub 1 plus sine theta E sub 2, and then E sub theta, defined by the other basis vectors, is cosine theta E sub 2 minus sine theta E sub 1. So that gives us a transformation table in which we have E sub 1, E sub 2, and we're defining E sub r and E sub theta as cosine theta, sine theta, and then minus sine theta, negative sine theta, cosine theta. So now we have everything we need to make those transformations back and forth between those vectors, or between those bases. The next thing that we need, we said, is the rotational relationship between these two reference frames, or the rotational velocity. And so that we need is omega b as observed in the inertial reference frame, and this is going to be theta dot, because that's our coordinate, and so theta dot is pointed in the E3 direction. Alright, so now we can move on to our kinematics. And so to define our kinematics, we need to define our point of interest. Where is the mass located? So for this, r p with respect to O is equal to, let's go back to our drawing. Okay, the point P related to O is just going to be L, and it's in the E sub r direction. So the length L in the E sub r direction. Now let's find our velocity in the inertial reference frame. The velocity of P with respect to O in the inertial reference frame is equal to d dt in the inertial reference frame of L in the E sub r direction. And so using the chain rule, we get L multiplied times d dt observed in the inertial reference frame of the unit vector E sub r. And because the unit vector E sub r is fixed within the polar frame, not within the inertial reference frame, we need to write this out, where we get L multiplied times the angular velocity of the reference frame B, our polar frame, as observed in the inertial reference frame, crossed with E sub r. So this gives us L, and we substitute in omega B as observed in inertial reference frame as theta dot in the EZ direction, crossed with E sub r. And so that's L theta dot, and EZ crossed with E sub r is E theta. So our velocity of point P in the inertia, as observed in the inertial reference frame, is equal to L theta dot in the E theta direction. So let's calculate our acceleration. Our acceleration of P with respect to O, as observed in the inertial reference frame, is equal to the time derivative of our velocity of P with respect to O, as observed in the inertial reference frame. And this is equal to the time derivative, as observed in the inertial reference frame, of our expression here. So we substitute this in, L theta dot in the E sub theta direction. And then let's go through the chain rule. Our first term, L is constant, theta double dot multiplied times E sub theta. And then we take the next one, L theta dot multiplied times the time derivative as observed in the inertial reference frame of E sub theta. And we've already pointed out that this is equal to omega B as observed in the inertial reference frame crossed with E sub theta. And so our expression is L, let's move this down, L theta double dot E sub theta plus L theta dot. We'll substitute this in. Our omega B as observed in I is theta dot EZ crossed with E sub theta. Continue with the algebra, and we get that this is L theta double dot E sub theta. And then we have L theta dot, and it's theta dot multiplied times theta dot, so it's theta dot squared. And then EZ crossed with E theta gives us negative E sub r. So it's negative E sub r. And so here's our expression of our acceleration of point P within the inertial reference frame. So now we have all the kinematics that we need, and they're all expressed within the polar, within the polar reference frame, or in this polar basis. So our next step, just like normal, is to create a free body diagram. So our free body diagram of our particle, we have our mass, we have gravity on this, and then we have our constraint force, F. And so there's really no other forces on this. We have, so when we add these up, F sub P, saying that these are all the forces that are on the particle, are equal to negative F in the E sub r direction. So it's the force, but it's in the negative E sub r direction. And then we're going to add to that mg, and mg is always pointed in the positive E sub 1 direction. Okay, so go remind yourself of that. And so we now apply Newton's second law, and Newton's second law says that all the forces on particle P are equal to the mass of that particle multiplied times the acceleration of that particle as observed in the inertial reference frame. So we can start plugging it in. So all of our forces are minus F E sub r plus mg E sub 1. Now I should point out here, notice that we've expressed this force in two different bases. We've got our constraint force expressed in the polar basis, and then our gravity is expressed in the inertial basis. And you're going to see this quite a bit, particularly with gravity, because remember, gravity is always pointing down when we are observing this in a reference frame that's fixed to the ground. And so we're mixing our bases, and that's okay. Don't let this concern you. On the right hand side, we've got the mass of our particle, and then we plug in our acceleration of point P as observed in the inertial reference frame, which we said is L theta double dot E sub theta minus L theta dot squared in the E sub r direction. Okay? So we got our mix of bases, and because we have our mix of bases, okay, E sub r and E sub 1, and then here we're both in our polar basis, we can't equate our scalars yet. Okay, so oftentimes when working, well, all the time when working in multiple reference frames, we're going to have to convert between the bases in our reference frames before we can start to equate our scalars. So what we want to do here is we want to convert E sub 1 into E sub r and E sub theta. You can do it the other way, in which you convert E sub r and E sub theta and E sub r all into the inertial basis. But let's go easy here and then convert E sub 1. So we go back to our transformation table, and we see in our transformation table, let's do that. Where is our transformation table? If we look at our transformation table, we see that E sub 1 is equal to cosine times E sub r minus sine times E sub theta. So let's just write that out, where we have E sub 1 is equal to cosine theta E sub r minus sine theta E sub theta. Okay, we're going to plug all this in, where we have negative F E sub r plus mg multiplied times cosine theta E sub r minus sine theta E sub theta. And all this is equal to our mass times L theta double dot E sub theta minus L theta dot squared E sub r. Alright, so now we can equate our coefficients and then get two scalar equations. So if we look at the E sub r coefficients, we'll get negative F plus mg cosine theta is equal to, and on the right hand side of the equation, all the E sub r coefficients are negative m L theta dot squared. If we equate our coefficients for our E sub theta direction, then we get negative mg sine theta is equal to, on the right hand side, we get m L theta double dot. And so what you should be noticing here is that we have two equations that come from this, but only one of them is the equation of motion. And how you recognize the equation of motion is because it is the one that has the second order parameter in it, which is theta double dot. So we see here that the equation of motion is here, and this other equation is giving us it's our constraint force equation. So we'll just call it a constraint equation. And what that allows us to do is, with this constraint equation, if we know theta and we know theta dot, if we know the state of the system, then we can solve for F and be able to calculate the force at any point in which this pendulum is swinging, as it swings back and forth. Our equation of motion, that's what we got before using our polar coordinates, And so when we rearrange these terms, you should recognize that we get 3 theta double dot is equal to negative g over L sine theta. All right, so in summary, what we've done is we've introduced a rotating reference frame, or another reference frame that's rotating within the plane of our inertial reference frame. We call this the polar frame. The polar frame is defined by a frame in which one of its unit vectors, one of its axes, points from the origin to the particle, or to the point that we're interested in, and it's always pointed in that direction. We've talked about transforming between reference frames, okay, setting up the transformation tables, and then we've applied that to our simple pendulum problem again. Now hopefully this was an easier way, once you get used to converting between these reference frames, hopefully you see that this is an easier way, which all we do is set everything up and use whatever bases that is the easiest way to define this problem. We need to take our time derivatives, always in the inertial reference frame. You got a couple tricks to be able to do that. And then there's really not any difficult differentiation to do, but we still end up with a really nice equation of motion that's easy to understand and easy to implement. All right, I'll see you in class.